Hello NMSys 2020 participants. Hello world. My name is Thomas Zinner and I am presenting our paper on using informed access network selection to improve HTTP adaptive streaming performance. The work was conducted together with Theresa Enghardt, the main author, and Anja Feldmann. In the following, I will turn off the camera. Today's user devices support different access network technologies, which can be used to connect to various content provided by internet services. Access networks we use in our daily life when using our smartphones are Wi-Fi and cellular networks. Typically, we can manually decide to use either cellular or Wi-Fi, and selecting the best network is non-trivial, as network conditions vary. A possibility to bundle the resources of various access networks on transport layers multipass TCP. It can aggregate capacity, but is not necessarily available on the server side. Further, it is application agnostic and not aware of client-side monitoring information, possibly resulting in a worse overall performance than when using only one interface. So, how to automatically select the best access network? Our approach to tackle this problem is to consider application needs specified by the application and network performance characteristics gathered during the network usage. Our informed access network selection, or IANS approach, is thus able to optimize for the most suitable network characteristics, such as highest available capacity or least perceived capacity variation. So, how shall IANS work for HTTP adaptive video streaming? Firstly, we use the socket intents prototype to enable applications like a video player to express intents when establishing a network connection. The prototype defines a set of specific intents which can be used to express application needs. In case of HTTP adaptive streaming, the best suitable access networks are selected on a per segment basis. For each segment, the video player application communicates the size of selected segment, that's the intent bitrate received, and the current buffer status via the intent buffer duration. IANS also continuously gathers network performance estimates, for instance based on previous segment downloads or other web downloads. Before sending out the application request for the new segment, IANS decides whether to use one specific network or both. After that, IANS places the transfer on the selected network. In the following, we will focus on how to design appropriate policies and evaluate the benefits of IANS compared to single interface usage and poor multipass TCP. When it comes to HTTP adaptive streaming, we want to achieve two goals. The first goal is to be able to load a video segment before the buffer is empty, so that no stalling occurs. The second goal is to reduce the segment load time to the best possible extent to enable the ABR to select a higher video quality. The design policies firstly select a candidate network to be used based on the capacity estimate of the last 10 seconds. That means the last few seconds. The final selection, however, is based on additional estimates and policy dependent. In the following, I'll present the main ideas behind the different policies. More details regarding the specific algorithms can be found in the paper. The first policy, the optimistic policy, values high capacity estimates over the last 10 minutes. Thus, it prefers good video quality for the risk of stallings. The second policy, the pessimist policy, aims to recognize sudden capacity drops. It checks if the segment can safely be downloaded given the capacity estimate of the last second, and if not, considers to use the other interface. The third policy, the selective MPTCP policy, mitigates the fact that MPTCP performance might be affected if not enough capacity is available on one of the interfaces. Thus, this policy uses MPTCP selectively when enough downstream capacity is available. Otherwise, the policy falls back to the usage of the network with the highest downstream capacity. In the following, I will present the used evaluation methodology. First, we used different video workloads using the DASH dataset provided by University of Klagenfurt. Particularly, we used the movies Red Bull Play Streets, The Famous Bunny and Valkama, and selected several different representations ranging from around 200 kilobits per second to 3 megabits per second, using a segment duration of 4 seconds. To guarantee similar lengths of the video clips, we used only the first 4 minutes of each video clip. Regarding the network conditions for the variable capacity scenario, we set network 1 to a constant capacity, following one of 7 possible capacity levels between 218 and 2118 kilobits per second. For network 2, we rely on 6 different variation patterns based on the 3G network traces from Horkon, Risa et al. And scale them to the different capacity levels, preserving the coefficient of variation. Our experiments cover a fractional design of all combinations of median capacity and capacity variation. For the cross-traffic scenario, network 1 is configured with a constant capacity of 2 megabits per second and network 2 with fixed 5 megabits per second. Cross-traffic is then injected using a varying number of concurrent TCP sessions, emulating different workloads using the Harpoon tool. With respect to the performance matrix, we rely on the directly measurable matrix for HTTP adaptive streaming, namely initial playout delays, representations played out, as well as the stalling events and durations. We mainly use the ITUT P1203 model for reporting the QE impact in the paper, but also validated the results using another model, the CQM model, which shows similar results. In general, we denote a QE lower than 3 a bad QE, while a QE of 3 or higher is called a good QE during this presentation. When conducting our experiments, we stick to the following order. After selecting the specific configurations, we conduct an experiment using ISO single networks, multipass TCP with default scheduler, the optimist policy, the pessimist policy, and then the selective MPTCP policy. We further conduct the measurements using 2 different adaptive bitrate algorithms implemented within GPEG, and each of the runs lasts for 240 seconds. Further, we repeat our experiments 5 times to assure statistical significance of our results. First, we start with the results for the capacity degree scenario, where the capacity of network 2 is fluctuating, but generally higher than the capacity of network 1 for the first 160 seconds. After 160 seconds, the capacity drops severely. Such a scenario may occur when a mobile moves out of the range of a wireless AP or stays within the range but experiences a low RSS. Median capacities for network 1 and network 2 are scaled using the different capacity levels. That means both networks provide the same median capacity during the 240 seconds of the experiments. As we can see, in case of very low capacities and also for low capacities, the usage of a single network results in a bad MOS score. Using only MPTCP does not improve the performance significantly, since MPTCP uses network 2 after the capacity decrease. Ions can help to improve the quality, particularly pessimist policy, resulting in a better MOS. In case of higher capacities, here, the selective multipass TCP and the pessimist policy outperform multipass TCP, the optimist policy, and also either single network usage. To sum up, the pessimist and the selective multipass TCP policy perform best in this scenario. Next, we investigate the Ferry scenario. This scenario is representative for the other investigated traces from the RESA dataset, since the results and corresponding conclusions are similar. Here, it can be observed that for low capacities, the usage of a single network still results in a bad QE. Further, using multipass TCP and the different policies results in a strong improvement compared to the single access network usage. Overall, the optimist and the pessimist policy perform good, and the MPTCP and selective strategies perform slightly better than the other policies. Let us now take a closer look at the cross-traffic scenarios. Here, we vary the number of concurrent TCP sessions over the wireless network 2, which provides a capacity of 5 megabits per second. Network 1, the fixed network, provides a capacity of 2 megabits per second. As we can see, the number of concurrent sessions has a strong impact on the video streaming quality when using only network 2. The IANS policies and multipass TCP are able to cope with an increasing number of concurrent TCP sessions and maintain a good video quality, whereas the optimistic policy is slightly impacted. To sum up, all approaches enabling a flexible adaptation, either by selecting the other network or using both parallel, are able to cope with the concurrent traffic in one of the networks. Let me now conclude my talk. In our paper, we presented our work on designing, implementing, and evaluating informed access network selection for HTTP adaptive video streaming. Particularly, we focused on different policies, the optimist, pessimist, and selective MPTCP policy, and compared these policies with static access network selection and poor MPTCP in a controlled testbed study. The study comprises a wide range of different network scenarios and also uses 2 APRs and 3 different video clips. The gained results suggest that optimizing for sufficient capacity and a low risk of variation is best, implemented by the pessimist policy. Further, it can be worse to selectively enabling MPTCP instead of enabling it per default, at least when using the default scheduler. Thanks a lot for your attention, and I'm looking forward to discuss with you during the Q&A session or via email. Keep care and stay safe. I'm looking forward to meeting you physically someday in the future.